Hello everyone. So last time we ended our discussion with discrete distributions. So let's have a insight into continuous distributions. Okay. So as we have discussed about random variables, how do they work? What does it mean? So we had left out something called as continuous random variables. If you think of these variables, these are the outcomes of the chances or the experiments that we do in a continuous manner, basically on things that we measure, right? So this can take values which are 0 0.1, 0 0.2, 0 0.0001, etc. etc. Okay. Now similarly, as the visualization of discrete variables, as you had only 4 5 lines for each of the probability measures, think that all of these values also need their own probability measures which are in between these discrete values. Okay, so each of them will have a probability measure which will make it a continuous graph. Okay, and as last time we were doing, if we had to calculate p x less than equal to 2, we could easily add p of 0 and plus p of 1 plus p of 2. For this case, you can't add for p of 1 and p of 2. You can't add p of 1 and p of 2. You have to add the whole region in it. Okay, and how do you add it? For that, the mathematical expression called as integration comes into picture. You have to add from 0 to 2, okay, whatever the function you have with respect to x, because we are doing on the x-axis. So this is what this integration means, to put it in plain English. Okay, so this way the discrete distributions visualization gets converted into continuous distributions visualization. Okay, now as this is the area of probability, the whole area, the sum of area, equal to 1, because the addition of probability is usually 1. Okay, now let's look at one kind of distribution which we also have discussed earlier, but this is called uniform distribution. Okay, what does it mean? Why is it called uniform? The reason of it being uniform, because for all the values of random variables that we encounter, the probability is same. Let's say Messi scoring a goal, the example that we took for discrete. Okay, the probability of him scoring 0 is equal to him scoring 1 goal, is equal to him scoring 2 goals, is equal to him scoring 3 goals. Okay, now all of the probabilities have a similar value, right? Now taking that concept into continuous variable or continuous random variable, rather, the example of Dhoni completing the run between the wickets, it could be 0.01 seconds or something for all the values of, right? So all of these will have similar probability, suppose. So this becomes a parallel line. If this become a parallel line, and as we said, this is the probability of, this area is the area of probability. area is now 1, or it will always remain 1 in all of the continuous distributions. Okay. So what we can also derive here is if the probability of, so if the number of a random variable increases, the probability also might decrease a bit. If you can think of the logic of how probability works, the sample size increases, so probability decreases. So more the random variables for one same experiment, the values of or the height of this graph would decrease, right? So now you are getting an idea of how do we get the area, height into length, area of a rectangle, correct? Right? Let's say the starting point is A and the ending point is B. Length becomes B minus 1, B minus A, sorry. Okay, and B minus A into its height equal to 1. So height equal to 1 by B minus A. So this value of Y is equal to H, which is 1 by B minus A, correct? Now the function of uniform distribution, the probability function or the density function is equal to 1 by B minus A, which is nothing but the height if X lies between B to A, or is equal to 0 for anything else. Right? Now what is the expected value? A plus B by 2. Some middle point. Mean always means that, right? So sigma, standard deviation, is equal to B minus A by root 12. Okay. Now suppose somebody asks you, what is the probability? This is A, this is B. Suppose these values are x1 and x2. What is the probability of these values lying between x1 and x2? How do you find out that probability? The probability of x is given by x2 minus x1 by B minus A. Isn't it logical? X2 minus x1, this area, x2 minus x1, finding out this area, correct? Now suppose, let's take an example. Bisleri company produces bottles, right, that weigh from 30 grams to 37 grams despite its effort to keep it uniform or have only one value, right? Now this supposedly is a uniform distribution, which means the number of 30 grams is probably equal to the number of 37 grams bottles produced in a lot or in a batch. Okay, now if somebody asks you what is the probability of a bottle lying between 31 and 35 grams, right, what you'll do 35 minus 31 divided by 37 minus 30. Right? Let's look at one example. Suppose the amount of time takes to assemble a plastic module ranges from 27 to 39 seconds, and that assembly time are uniformly distributed. Describe the distribution, right? Which means you find the mean, you find the standard deviation. Okay, and also what is the probability that given assembly will take between 30 and 35 seconds, and also the probability of fewer than 30 seconds. Okay, quite simple. You might take a pause here and try to solve it. Similarly, question number 2. According to National Association of Insurance Commissioners, the average annual cost for automobile insurance in the United States in a recent year was $691. Okay, suppose automobile insurance costs are uniformly distributed in the United States with a range of from 200 to 1182. So what is the standard deviation of this uniform distribution? Okay, what is the standard deviation? What is the height of the distribution? What is the probability of a person's annual cost of automobile insurance between 410 and 825? Okay, pretty straightforward question, right? Similarly, let's look at one more distribution, which is called as normal distribution. Okay, so as the name suggests, it is pretty normal, which means in most of the cases, normally you get this kind of curve, or the data tends to populate around the center. A normal curve is formed. Okay, these two never meet. It is symmetric about the middle point. It is bell-shaped, and it is unimodal in nature, right? This normal distribution, the invention of it is attributed to someone called Carl Gauss, right? Same guy who went through Gaussian or gave us Gaussian distribution. Okay, normal curve is also sometimes referred to as Gaussian distribution in special conditions. Okay, you don't have to worry about it, but just for your knowledge, whoever is more interested to understand this. Okay, now similarly, as for uniform distribution or discrete distributions, we always had a probability function or the probability density function, or the function with which you can plot the graph. We also have a function for normal curve. This is pretty complex, and you don't have to remember it as such, but just for your knowledge. Formula is somewhat this complex. Okay, the pi and e values are the same constants from mathematics. This is 2.71, this is 3.14. This is sigma standard deviation, this is mu, this is the same sigma. Okay, 2 sigma whole square. Right. Now when we do a standardization of normal distribution, the function differs a bit. It becomes e to the power minus x square by 2 divided by root over of 2 pi, because mu equal to 0 and sigma equal to 1, which brings out the concept of z. Okay, because every mu and every sigma will have a different normal curve. Correct? Now to standardize all of them, we can use something called as z, which is equal to mu x minus mu by sigma. This value converts it into this form, which converts this into this form. Right? Pretty simple. Okay. Now, you would probably find it more easier to understand that the area under this graph, this curve, is also equal to 1. Half being 50, other half being 50, because it is symmetrical in nature. Okay. Two more questions for you to solve for normal distribution. Question number 1, take a pause and solve this. Then question number 2, take a pause and solve this. Right? So I guess now this video could be completed much faster, because we have the basic concepts of probability and how the density function works. How does the probability density function get populated, or how do we visualize it? Right? So this is about continuous distributions. Okay. Now uh, let's discuss about something called as sampling. Right? And because we have already studied about probability and the way probability works, we would work with concepts of random sampling. Okay, random sampling only. There are mostly three types of random sampling. One is simple random sampling. Second is stratified random sampling. Third is cluster sampling. Okay, simple random sampling is just randomly picking out. So suppose we have 1000 data points and I have to pick 100. Okay, I'll randomly pick any 100 out of those 1000. Okay, the same function which is used in Excel or Java or Python is called as a random function. Okay, now what is stratified sampling? Suppose this is to uh, find the all-rounders in class. Okay, there are 5 sections. Okay, how do I select them? So from each of the section, I'll select 20 guys. That is called stratified random sampling. Now what is cluster sampling? I'll go to a place where everybody is singing the national anthem. Select the line of that class and randomly choose 100 from them. That is called choosing from a cluster. Okay, we will use some of these sampling concepts as we go ahead and read machine learning. Okay, one more simple concept that we can learn here is uh, central limit theorem. Okay, so what does it mean? Think of a case where you are collecting samples. You have done a sampling method, you are collecting samples from a population, right? Uh, let's say you are selecting the mean of scores by Indian batsmen in every series. Okay, now the mean of scores would be 75, 30, 45, 50, 55, anything, right? The means would vary. Okay, now we take all of these mu values and plot it in a graph. We call this a sampling distribution of means. Okay, so now why do we do it? Because if we do this and then we find the mean of this new developed distribution, it gives a very fair idea about the population mean, or we also call it population parameter. Okay, now why is it important, and what is the central limit theorem exactly? It states that no matter what is the distribution of the population, is this, this, it is this, whatever is the distribution of the population, the sampling distribution of the mean approaches normality. Okay, and this happens for a fairly good amount of means that we extract, and that number is seen to be greater than equal to 30. If you calculate the means more than 30 or times, then it approaches near normality, right? So this is the central limit theorem. Why is it useful? Because it is useful because we found a way to deal with the unknown distributions. Okay, we found a way as in because we have learned normal distribution a lot. We know the logic behind it, and we could form different ideas by working on that distribution, right? So which is why central limit theorem becomes more important. So going ahead, after we see this video, and in the next class we'll take this concept or the concepts that we learned till now bit higher. Okay, see you in the class.